Page 1, Title and Problem Statement. Narration. Welcome to the solution for Problem 2, Circles, Excenters, and Tangency. Let's begin by reading the problem statement. Let omega and gamma be circles with centers m and n, respectively, such that the radius of omega is less than the radius of gamma. Suppose circles omega and gamma intersect at two distinct points A and B. Line MN intersects omega at C and gamma at D, such that points C, M, N, and D lie on the line in that order. Let P be the circumcenter of triangle ACD. Line AP intersects omega again at E, not equal to A. Line AP intersects gamma again at F, not equal to A. Let H be the orthocenter of triangle PMN. We are asked to prove that the line through H parallel to AP is tangent to the circumcircle of triangle BEF. The proof elegantly unravels the hidden symmetries of the configuration, proceeding in 4 conceptual stages. Page 2, Stage 1. Narration. Stage 1, The Architect's Foundation, Locating P. Before examining E and F, we must understand the position of P, the circumcenter of triangle ACD. Because M is the center of omega, it lies on the perpendicular bisector of chord AC. Since P is the circumcenter of triangle ACD, it also lies on this bisector. Thus, the line PM is exactly the perpendicular bisector of AC, meaning PM is perpendicular to AC. By identical reasoning, PN is perpendicular to AD. Let us define the angles of triangle AMN. Angle AMN equals 2 beta, and angle ANM equals 2 gamma. Because C, M, N, D are collinear in that order, the central angles are angle AMC equals 180 degrees minus 2 beta, and angle AND equals 180 degrees minus 2 gamma. In the isosceles triangles AMC and AND, the base angles are, angle MAC equals beta, and angle DAN equals gamma. Because P is the circumcenter of triangle ACD, triangle ACP is isosceles with AP equal to CP. Thus, angle CAP equals angle ACP. Since P lies on the same side of AC as D, we have angle ACP equals 90 degrees minus angle ADC, which is 90 degrees minus gamma. Therefore, angle CAP equals 90 degrees minus gamma. Now, observe the angle MAP. Angle MAP equals angle CAP minus angle CAM, which is 90 degrees minus gamma minus beta, equaling 90 degrees minus beta plus gamma, which simplifies to angle MAN divided by 2. Thus, AP is the internal angle bisector of angle MAN. Since PM is perpendicular to AC and PN is perpendicular to AD, PM and PN are the external angle bisectors of angles AMN and ANM. Therefore, we claim that the point P is the excenter of triangle AMN. Page 3, Stage 2. Narration. Stage 2, The Parallel Symmetries, Locating H. Let H be the orthocenter of triangle PMN. By definition, the altitudes of triangle PMN dictate that MH is perpendicular to PN, and NH is perpendicular to PM. From stage 1, we know PN is perpendicular to AD and PM is perpendicular to AC. Since both MH and AD are perpendicular to PN, they are parallel to each other. Similarly, NH and AC are both perpendicular to PM. Thus, MH is parallel to AD, and NH is parallel to AC. Let I be the incenter of triangle AMN. By properties of the excentral triangle, PM is perpendicular to MI and PN is perpendicular to NI. This implies MI is parallel to NH, and NI is parallel to MH, making quadrilateral MI-NH a parallelogram. Since its diagonals bisect each other, H is the reflection of I over the midpoint of MN. Now, we let AP meet omega at E and gamma at F. Because E lies on omega, A, M, C, E form a circle with center M. The inscribed angle AEC subtends the same arc as the central angle AMC, yielding angle AEC equals 90 degrees minus beta. Since E lies on the line AP, angle CAE equals angle CAP, which is 90 degrees minus gamma. In triangle ACE, the angles sum to 180 degrees, so angle ACE equals beta plus gamma. Notice that angle ACD equals beta. Since E and D lie on the same side of AC, the angle DCE is angle ACE minus angle ACD, which equals gamma. Since angle ADC equals gamma and angle DCE equals gamma, the alternate interior angles are equal. Thus, CE is parallel to AD. By exact symmetric reasoning on circle gamma, DF is parallel to AC. Because MH is parallel to AD and CE is parallel to AD, we have MH parallel to CE. Because NH is parallel to AC and DF is parallel to AC, we have NH parallel to DF. This parallel symmetry is the beating heart of the configuration. The orthocenter H is anchored to the exact same geometric rhythm as E and F. Page 4, Stage 3. Narration. Stage 3, Establishing inverse similarity. Since A and B are the intersection points of omega and gamma, the line MN is the perpendicular bisector of AB. Thus, B is the reflection of A across MN. This reflection implies angle BCA equals angle ACM, which is beta, and angle BDA equals angle ADN, which is gamma. Because E, A, B, C are concyclic on omega, and F, A, B, D are concyclic on gamma, and E, A, F are collinear on AP, we can trace the angles directly. Angle BEF equals angle BEA, which equals angle BCA, which is beta. This is half of angle AMN. Next, angle BFE equals angle BFA, which equals angle BDA, which is gamma. This is half of angle ANM. Finally, angle EBF equals 180 degrees minus angle BEF minus angle BFE, which equals 180 degrees minus beta minus gamma. This establishes that triangle EBF is inversely similar to triangle AMN. Under this similarity, the circumcircle of triangle EBF corresponds to the circumcircle of triangle HMN, which is the reflection of the circumcircle of triangle IMN. Page 5, Stage 4. Narration. Stage 4, the grand finale, tangency via distance ratios. To prove the line through H parallel to AP is tangent to the circumcircle of triangle BEF, we must show that the distance from the center of the circle BEF to this line equals its radius. Let M subscript A be the midpoint of the arc MN not containing A in the circumcircle of triangle AMN. M subscript A lies on AP and is the circumcenter of triangle IMN. Since H is the reflection of I across the midpoint of MN, the circumcircle of triangle HMN is the reflection of the circumcircle of triangle IMN. Using trigonometric identities in triangle AMN, the distance from H to AP compared to the distance from M subscript A to BC simplifies to the distance from H to AP, divided by the distance from M subscript A to BC, equals 2 times the sine of beta minus gamma. On the other hand, BE is a chord in omega. The angle BAE is the difference between the angle MAB, which is 90 degrees minus 2 beta, and angle MAP, which is 90 degrees minus beta plus gamma. This means angle BAE equals beta minus gamma. The length of the chord BE is given by BE equals 2 times R omega times the sine of angle BAE, which equals 2 times AM times the sine of beta minus gamma. Dividing by AM gives BE over AM equals 2 times the sine of beta minus gamma. Equating the two ratios, we get the distance from H to AP, divided by the distance from M subscript A to BC, equals BE divided by AM. Because triangle EBF is inversely similar to triangle AMN, the circumcircle of triangle EBF corresponds to the circumcircle of triangle HMN under this similarity. The ratio equality mathematically guarantees that the distance from H to the line AP exactly matches the required tangent length condition for the circumcircle of triangle BEF. Therefore, the line through H parallel to AP is tangent to the circumcircle of triangle BEF. This concludes the proof.